Hey y'all, this lesson is on hypothesis testing for one population mean when the population standard deviation is unknown. So in this case, instead of using a standard normal curve and z-scores, we'll be using the t-distribution and t-scores. So it's a student t's distribution. And if you'll recall from one of my previous lessons, when we look at the T tables, we have to consider the degrees of freedom, which is found from taking n minus 1. So that's going to help us today on this lesson. Now I have a little review up here at the top of how to find a t-score. And it's very similar, you'll see, very similar to the z-score. The only difference is we don't have sigma, which is the population standard deviation. We instead have this sample standard deviation, and the symbol for that is S. So this is the formula used instead. And I did make a little typo in the notes down here I want to point out before we get into it. Down here on step 4, this is supposed to say t-score. Oops. So we're going to do the same exact process that we did for when the population standard deviation was known, except instead of z-scores, we use t-scores. So we have I think the same problem as my previous notes. We've got our sample mean, our sample size, the sample standard deviation, population mean, and our our null hypothesis and our alternative hypothesis. And I'm curious to see how this differs from the z-test because it's the same exact information, but now it's a t-test. So if we were to restate the null and the alternative, the null is that the population mean is equal to 22, and the alternative is it's less than 22, which indicates a left, I should write that prettier, a left-tailed test. So we have our little curve, and then it's alpha 0.05 and it's left-tailed. So that 5% is our alpha value that we're going to use to help us make a decision. Remember, you can't make a decision until you know the significance level. So we're going to compute the value of the test statistic. That's the value that we're comparing to our cutoff point. That's going to be 20 minus 22 over 4 square root 32. And then I believe that value is negative 2.82, but let's just check and see. Go here so you can see what I'm typing in. Let's see. Okay, we have 20 minus 22 over 4 divided by square root n. Get it out of the square root. Hopefully that worked. I think I'm good. Negative 2.83. This was a little off. And then we need to find, if we're going to do the critical value approach, we need to find the cutoff point. So the cutoff point, the critical value, sets up your rejection and your non-rejection zones or regions. And if your test statistic is in the rejection region, then we reject the null hypothesis. But we need to figure out where that point is. So these are t-scores because we were given the sample standard deviation. And that's how you would know if maybe all these questions were jumbled on a test with z-tests and t-tests, then you know which one you're needing to find based on what information was given. If you're given a sample, you're going to use the t-test. So for the t-test, you do have to know the sample size. Sample size, n equals 32. which means that your degrees of freedom is 31. And so if you're using the T table, you have to know that the degree of freedom is 31. And we also need to know the alpha value. So this is a left-tailed test. So we're going to need the area to the left with a degree of freedom of 31. So if you look at the T table, you'll go T sub alpha 0.05, that's our little tail, and degrees of freedom 31, or you can go to the calculator and go to second vars inverse T and type in your alpha and your degrees of freedom, and we get negative 1.696. Negative 1.696. Our test statistic was negative 2.83. So if we were to draw our picture with our curve, you would now decide if negative 1.696 is the cutoff, is negative 2.83 past the cutoff? Yes, it is, which means it puts it in the rejection region. So if you're having trouble picturing that, oops, sorry, you might draw your curve. Here's 0, 1, 2, 1.696 is here. That's my cutoff. And then negative 2.83 is over here, which is my test statistic. So it is in the rejection region. And in the p-value approach, we find the p-value associated with our test statistic. So the area associated with negative 2.83, and we compare that to our alpha level. So go ahead and find that. Finding the p-value associated with this t-score is a little different than what we've been used to with the normal CDF. So normal CDF is based on a normal curve. And this is not a normal curve because it's a t distribution. So it's a t curve. So if you look in your calculator, you should find when you go to second vars, if you go down a little bit further, you see t CDF. And that is the t curve. And what you need to tell the calculator is that it's the t curve. You need to tell it the area you're looking for, and then you need to tell it the degrees of freedom. So let's see if I can find that on this calculator. I'm going to go to second vars, and mine is number 6. It's T CDF. And you can see on mine it says lower, upper, and then V is degrees of freedom. So my lower, this was a left-tailed test, I believe. So we're going to go lower value, upper value, and the degrees of freedom in this one were 31. And we get 0.004. So go back here, my p-value is about 0.004. And then if p is less than alpha, I've been using less than alpha. It's actually less than or equal to, but that's okay. It's kind of a given because if it's anywhere in the, anyway. So p is 0.004. Is that less than 0.05? Yes, it is. So we reject. That confirms that we reject. So you remember, you don't have to do both approaches. You can just pick one. So at the 5% significance level, we do have sufficient evidence to reject the null hypothesis in favor of the alternative hypothesis. So I'm curious, I can't remember what it was in the last video. It was still reject. Cool. Sorry, I was just curious about that. So everything's the same as when the population standard deviation is known, I mean, not everything's the same, but like the process is the same. The only difference is we're using the T curve instead of the Z curve, the standard normal curve. So our values that we're using as our cutoff points and our areas are going to be a little bit different than if we were to use Z. So let's go to the next page. And as with everything, you can do this in your calculator. It is called a t-test. So you're going to go to Stat and then over to Tests, and you're going to click t-tests. And then we are inputting stats. So let me just show you. I'll show you the steps. You're going to go to Stat, over to Tests. This is a t-test. It's stats. I'm going to input my population mean, my sample mean, my sample standard deviation, and the number of samples. And then this is left-tailed, calculate. And this gives us everything we just found by hand. So it gives us our T, our critical, our T value, our P value, and then we can use those values to make our decision. So our T value was about negative 2.83. This was 0.004, 20, 4, 32. Our alpha level is 0.05. And again, this is one reason why I like to do the p-value approach, is because if you're doing it using the calculator, then there's your p-value, there's your alpha, compare those, and make your decision. If you don't like the p-value approach, then you can go on to find the critical t-value based on alpha and compare those. And I think our critical t-value was negative 1.696. And it's still reject. So at the 5% significance level, we do not have enough data. I'm sorry, we do provide sufficient evidence to reject the null hypothesis. This last example here is, I actually ended up giving you the information you needed, but let's pretend like this was all you were given. In 2005, the average person watched 4.55 hours of TV a day. A random sample of 20 people gave the following numbers. And so let's pretend like they just gave you that data and you had to run a test. So before you can run your test, you would have to find the sample mean and the sample standard deviation. Now remember that you don't have to do that by hand. You can use your calculator. You would go to 1var stats. So you would input your data, go to stat, 1var stats, and then that would give you the information you needed. You need the sample mean and the sample standard deviation. But since that wasn't the point of this lesson, I went ahead and gave it to you down here, which means now you can set up your hypothesis test and make a decision at the 10% significance level with a sample size of 20 and a mean of 4.55. So I want you to try this one on your own and then come back and check your work. So after reading this one, you should see that this is a two-tailed test because it is, do the data provide enough or sufficient evidence to conclude that the amount of TV watched per day last year by the average person differed from that of 2005. So when it says differed, then that means your alternative hypothesis is not equal to what they think it is, which sets up a two-tailed test. And so if you're using the critical value approach, then you have to consider that when you go find your t value. Whether you're using a t-table or a calculator, if you draw that picture, it's a 10% significance level, but when it's two-tailed, we're splitting up the 10%. And so you're going to go to inverse T, you're going to type in 0.05 and your degrees of freedom, and you'll get that negative 1.729. And that's one side, and the other side is symmetric. So that's our cutoff point. And then the value of our test statistic is based on the sample mean. So that's 4.76 minus 4.55 over standard deviation divided by square root n, which was 20, I believe. Yep. And you should get about 0.41. So at this point, if you did this critical value approach, you can draw your picture and compare those values. Is 0.41 in the rejection region? No, it is not. 0.41 is like here. And that's firmly in the non-rejection region. Now, if you did not do the critical value approach, if you went ahead and did the t-test, then in your t-test from your calculator, you would find a p-value of about 0.69 with an alpha value of 0.10. And since p is not less than or equal to alpha, then we do not reject, which goes along with the critical value approach. It's in the non-rejection. So at the 10% significance level, the data does not provide sufficient evidence to reject the null. We cannot reject the null because there was a high enough probability based on our significance that if the null were true, this is the probability of getting this test statistic. So it's pretty high, which means we can't reject the null hypothesis. So that is the t-test and the t-distribution, hypothesis testing, not knowing the population standard deviation. So it's very similar to the z-test. It's just using a little bit different formula and a different curve. So I hope this helped. If you have any questions, please let me know and I will be happy to help.